Hello and welcome to this second lesson in the equilibrium and redox reaction section, and this one's called Compromise Conditions in Industry. It has specification reference 3.1.6.1 and our learning objective, singular, for this lesson is we want to be able to explain why, for a reversible reaction used in an industrial process, a compromise of temperature and pressure may be used when making a chemical, for example. Okay, so to illustrate this concept, why don't we look at an actual reaction? It's the reaction that makes ethanol via a reversible reaction between ethene and steam. And the thing to remember is that when companies are making products such as ethanol, there's two things they have to consider. One, of course, is the money they're going to get for selling the ethanol, and two is the cost of making that ethanol. And the cost of making that ethanol rather depends on how they run the reaction. So at what temperature they're going to run the reaction, what pressure they're going to run that reaction, and if they choose a particular temperature and pressure, how much ethanol is going to come out at the end that they can then sell. So let's write this reaction down first. We've got some ethene to start with. And we're reacting that with some steam. And that's in equilibrium with the product ethanol. And this reaction happens to be exothermic to the tune of 46 kilojoules per mole. Okay, so not surprisingly, the sort of conditions that we're going to consider are those conditions that we studied in Le Chatelier's principle, because really what we're doing here is we're applying Le Chatelier's principle to the production of ethanol. So first of all, let's use a table like we did before to consider some of the conditions that we can alter to make the most efficient reaction. Most efficient in terms of production of ethanol. We want to maximize the production of ethanol so we can maximize our revenue, but at the same time we want the reaction to be cost effective. So let's deal with temperature first, shall we? And for illustrative purposes, let's just assume that we can either have a low temperature or a high temperature. And what we're going to do is we're going to consider the effect of low and high temperatures on a couple of factors like the equilibrium position, and the reaction rate. Okay, so why might we be interested in the equilibrium position of this? Well, if we're interested in making ethanol, which is the product as written here, then really we want the equilibrium position to be as far to the right as possible. When we're using the raw materials, ethene and steam, and we want to convert those into ethanol. So we want the equilibrium position to be as far to the right as possible. We want the yield, which is the amount of product you're making, to be as high as possible. That's what we want, and so that's why we're interested in the equilibrium position. So let's say we operate the reaction at a very low temperature. Which reaction is that going to favour? Is it going to favour the forward reaction to create a high yield, or is it going to favour the backward reaction to create a low yield? Well, it's an exothermic reaction, isn't it? So when we decrease the temperature, we're taking heat out of the system. So that's favouring the forward reaction. So let's write that down. So this favours the forward reaction, and that gives us a high yield, which is good. That's what we want. For completeness, let's consider the high temperature. If we crank the temperature up really high, how's that going to affect the equilibrium position? Well, high temperatures favour endothermic reactions, and the endothermic reaction in this case is the backward reaction. So a high temperature, if we operated the reaction at a high temperature, our equilibrium position would move to the left and produce a low yield. So let's write that in. So that favours the backward reaction. Leading to low yield. Which is not so good. Even though I've written it in green, I should have really chosen those colours the other way around. Never mind. Okay, so, however, high temperatures, as we know, they favour fast reactions, don't they? And fast reactions are good. So what? So if you crank the temperature up, your reaction rate would increase and you would make more product, despite what's happening to the equilibrium position. So fast reactions are good. Whereas if we made the temperature very low, what we would do is we would slow down the reaction rate. So even though the yield, the equilibrium position is far over to the right, so we're making a high yield, so most of our reactants are being converted into product, that's happening so slowly that might be a problem. So you can see there's a compromise here, isn't there? The industrial chemists, the chemical engineers are going to want to have high temperature for reaction rate, but they're going to want low temperature for equilibrium position. So there's going to be one temperature, there's a balance of both factors, so that you're going to get the right amount, the best amount of ethanol out of that reaction. Okay, so that's one compromise that chemical engineers might have to make. The other one would be to do with pressure. So let's draw another table and consider pressure. And in the same way, let's just make it simple. So we'll consider low pressure and high pressure. And again, what we want to do is we want to consider the effect of that pressure change on the equilibrium position. But also on the cost this time. Okay, so pressure in a gaseous equilibrium reaction is all about number of moles on the left and number of moles on the right. So let's just count up. We've got on the left 2 moles. 2 moles of reactants and 1 mole of products. So if you remember from our section on Le Chatelier's principle, if we increase the pressure, we're going to want to make fewer moles, which would counteract that change and decrease the pressure. Okay, so an increase in pressure is going to favour the forward reaction. Let's write that in. So that high pressure favours, in this case, the forward reaction, leading to high yield. Which is what we want. And the corollary of that, of course, is low pressure. If we were to decrease the pressure of that equilibrium, the Le Chatelier says that the equilibrium position would change to counteract that decrease in pressure by making more molecules, and it does that by shifting to the left. So low pressure favours the backward reaction, the leftward reaction. And that would decrease your yield. Okay, now so why don't we just crank up the pressure then? Well, the thing about high pressure is that the high pressure vessels are very expensive. They require thick steel, strong steel, and the pumps that are required to make that pressure need to be very powerful and therefore very expensive, and the gaskets that seal all the joins in the equipment need to be use very expensive materials. So high pressure vessels cost a lot of money, so the cost is high, whereas low pressure vessels can use less expensive materials. Everything about them is lower cost. So that is good. So as you can see, we've put all the good things in red and all the bad things in green. And so just as we had a compromise with temperature, we have a compromise with pressure. So in an ideal world, we'd have high pressure, and that would favour the forward reaction, get a high yield. But at some point in time, as you make the pressure higher and higher, it's going to get too expensive to make the equipment. So we need to compromise there a little bit on with cost. Okay, so what happens in industry? They try hundreds of different variations of temperature and pressure, first theoretically and then practically, and they come to a conclusion and they make their product. And in this case, in industry, ethanol is made with a pressure so the pressure is about 60 to 70 atmospheres, and 1 atmosphere is about 100 kilopascals, so that's about 6,000 to 7,000 kilopascals. And the temperature that's settled upon, right, is about 300 degrees Celsius as a compromise between equilibrium position and reaction rate. So that compromise is another interesting thing. That compromise in temperature is helped a little bit because what you want to do is you want to use as low a temperature as you want because it's an exothermic reaction. But you don't want to slow the reaction down until it stops, because you actually have got to produce some ethanol to make some money. So to increase the reaction rate, despite the fact that the temperature is low, what you're going to do, you're going to use a catalyst. So in industry, we make up for the fact that relatively low temperatures are being used in this exothermic reaction by using a catalyst. And the catalyst that works particularly well in this case is phosphoric acid. And there we are. That's the compromise decisions that chemical engineers make when they're making ethanol. So another industrial process that is in the spec for us to learn is methanol production. And it's made from hydrogen and carbon monoxide, according to the following reaction. So we're going to start off with some hydrogen gas. Okay, we're going to react that with carbon monoxide, and that's in equilibrium with our methanol. And the important thing is to look at whether this reaction is exothermic or endothermic in the forward direction. And as usual, it's exothermic. Most reactions are exothermic. So the compromise decisions are going to be very similar to the ones made on the previous slide. So we're going to have a compromise between temperature. You're going to want a low temperature for the equilibrium position, but you're going to want a higher temperature for the reaction rate. And look, you've got 3 moles on the left-hand side and only 1 mole on the right-hand side. So you're going to want a high pressure for yield, and yet high pressure is quite expensive. So you've got exactly the same compromises. And what happens with methanol by theory and then experiment is that the pressure that is found to work the best is between 50 to 100 atmospheres, and a temperature of about 250 Celsius, and of course the catalyst, so that we can get away with a low temperature without decreasing the rate too much. We use a catalyst, and in this case the catalyst that works particularly well is a combination. It's a mixture of copper, of zinc oxide, and aluminium oxide. So it's a mixture of those 3 metal compounds, and that is the conditions under which methanol is made in industry today. So this was quite a quick lesson. We just had one learning objective. Let's see, remind ourselves of it, see if we've satisfied it. We wanted to be able to explain why, for a reversible reaction used in an industrial process, well, we've considered both ethanol and methanol. Why a compromise of temperature and pressure may be used, where the compromise of temperature is yield versus rate, and the compromise to do with pressure is, depending on the number of moles, is going to be yield versus cost. Okay, and you balance those 3 or 4 things to get optimum conditions, so that you're producing the maximum amount of valuable product at the lowest cost. And of course, don't forget the catalyst. Don't forget the catalyst that makes up for the fact that for an exothermic reaction, i.e. most of them, you want low temperatures, but you don't want to slow the reaction rate down too much, so you use a catalyst. There we are. Thank you for listening. Hopefully that's been clear, and I'll see you in the next video lesson.